today we have the pleasure of hosting Jianxiong and Jinliang from Jianxiong and Jinliang from Tsinghua University, from the Air Lab as well, the AI Institute. They are both advised by Professor Zheng and Professor Jinliang Liu, as well as Professor Jianxiong. So Jianxiong research interests are broadly lies in the advanced data-driven learning algorithms and decision making, such as offline reinforcement learning, offline imitation learning, reinforcement learning from human feedback, as well as the promising applications in embodied AI. The research interests of Jinliang lie broadly in computer vision, multimodal model, and embodied AI. And today I think we have a first paper that's more on offline RL, and then some mention of extended work that can also apply to embodied AI. So thank you very much, guys, for coming to present, and we're looking forward to your presentation.
Okay, so thank you for the introduction, and very nice to meet you. Today, I'm very happy to share something about towards generalizable and sample efficient embodied AI with Jinliang. And everybody knows that in recent years, there are a huge advancements in artificial intelligence, that we have many exciting breakthroughs about the ChatGPT or the GPT-4. But if we think back, what about breakthroughs in decision making? Okay, so if we only consider the narrow scenarios like the gaming AI that has perfect simulators, the answer is absolutely yeah. The decision making works pretty well in the simulator. But when it comes to the real world applications like the real world robotics or the autonomous driving cars, actually it's hard for us to actually see a real application that deploys RL algorithms on that. Mostly till now, the most autonomous driving cars are still rule-based. That, for example, we just hard code the driving rule using some if-else or something like that, not the RL or imitation learning algorithm. So basically, till now, the embodied intelligence is still in its beginning stage. Like for the AlphaGo, yeah, the AlphaGo can outperform the human champions. It can outperform the human champions. But in that context, the AlphaGo still needs a human to help to move the chess. So when the embodied AI is deployed in the physical world, it's still in its beginning stage. So why is embodied intelligence so challenging? Why is it so hard? And basically, we want for embodied intelligence, we want to train a very powerful and very generalizable robot policy that can help us do many things, like cleaning the room for us, or even making a breakfast for us, or maybe taking care of baby for us, many stuffs like that. So the most standard way to achieve that ultimate goal is typically we first collect many human demonstrations using some teleoperation systems like the VR or mobile Aloha, something like that. And then we typically train a very large vision, language, and action model using that collected data in an end-to-end way. And then we deploy the robot. But in the physical world, the data collection is quite challenging compared to in the digital world, like the language model. In the internet, we can easily collect the trillions of conversation data to train a good language model. But in the physical world, it's hard for us, especially for the academics, to employ to hire many people to help collect data for us. So basically, the data is very limited. It's not enough. It's far beyond far away from the enough data quantity to train a good vision language model. So this this robot learning pipeline is not that efficient for us to train a robot policy. But on the other hand, actually there are already many cheap and diverse out-of-domain data, like the human manipulation data. The humans are doing the household work every day, and you can collect many such that data on the internet, like this one. And actually, although the embodiment in these videos are not different to the robot embodiment, but these videos actually already have many usable information for robot learning. For example, by watching these videos, the robot can somehow understand how task progresses for different language instructions. And also, these videos tell something about the world dynamics or the physical laws, like how do different objects interact with each other. So we wonder, what if we first extract these useful features or useful representation from this out-of-domain data first, and get some pre-trained multimodal representations. This pre-trained multimodal representations encode many useful information for the downstream policy learning tasks. And then we use this representation and collect only a small number of robot data to achieve the efficient and generalizable robot policies. And so basically, this is our first work. We call that DecisionNCE, embodied multimodal representations via implicit preference learning. And this work is accepted by ISMO 2024, and also is selected as one outstanding paper and the workshop in ISMO. Okay, so if we want to pre-train some multimodal representations, and the most standard approach to achieve this objective is using some contrastive learning objective like the clip, just to align the test modality and image modality together. But things becomes a little bit different here because, for the text instructions in decision making or in embodied intelligence, the instructions mostly describe some dynamical movements instead of some only static images like a dog or a cat. So it basically describes some movements like open something, move something, or push something. So it cannot simply be aligned with some static images, but with some movable or dynamical trajectories that can reflect these dynamical movements. So in embodied intelligence, we do not need the standard clip contrastive representation, but we actually require some trajectory level contrastive learning that aligns the textual instructions with the trajectories, not the static images. So basically, to achieve this, we found that in the popular predatory model, in the reinforcement learning from human feedback domain, and this objective actually naturally offers a good solution. So take a deep look at this objective, and we can see that humans are required to react to trajectory segments, like the sigma positive is more preferred than the sigma negative. And the sigma here denotes some trajectory segments sampled from like a video. And to train the model to align with this human preferences, and a reward model is required to train to increase the total rewards for the positive segments and also decrease the total rewards for the negative segments. So we can see that this objective actually performs some kinds of trajectory level contrastive learning by compare the positive segments and also the negative segments. So this objective, in principle, can be applied in the decision-making setting to train some multimodal representations for decision-making. Yeah. But there are still some challenges that need to be solved. And first one is how to get the preference annotations. For example, humans are required to rank two different directories, but you know, for the existing data sets, actually we do not have enough such annotations to give such rank. So collect many human preferences may be very costly. And also this objective, this predatory model is designed for reward learning, not for representation learning. So how to transform this reward learning objective into a representation learning objective? Or in other words, how to connect the reward function here with the representation that we are interested to transform this reward learning to a representation learning objective. And the third one is the segment length is hard to select. For example, if the segment here is too short, then it may be very hard to cover some long horizon information that captures the global task progressions. But if the segment here is very long, then when we try to calculate this reward summation, we must inference the image encoder for every frames in a video. So it may be very computational inefficient, and also it may introduce a lot of noise in the intermediate frames. So basically, for the first challenge, how to collect the human preference annotations, and we must know that the language actually is already a way for humans to communicate their intentions to the robots. So we can naturally assume that the videos or the video segments are more preferred than the others for the matched language annotations. For example, the video for the open refrigerator is naturally more preferred for the video for pick up the pot if the human give this instruction command. So actually, so under this assumption, existing datasets already have a lot of such implicit preference annotations that have not yet to be fully exploited. So we do not need additional cost to label this kind of human preferences anymore. We just need to use this assumption to label the human preferences. Yeah. And also for the second question, how to transform the reward learning objective into a representation learning objective. And our solution is straightforward and simple. We can just reparameterize the reward in the representation space. Or in other words, we can design the reward function as a function of the representations. So the gradient to optimize the reward can backward through the representations to optimize the representations. And we first try to utilize a simple and a common design choice called the potential-based reward. And this reward just want to encourage is the frames in a video just gradually moves towards the language instruction. For example, this dot represents the image representation of the first image frame, and then after the video gradually progresses, the image representations that also gradually moves towards this language instructions to align with this language instruction. So under this reward reparameterization method, we actually introduce some human inductive bias about the final images are more aligned with test instructions, because the final images will be the most closest to the language instruction under this formulation. But this is not what we really want, because we have just said that in the embodied intelligence or in decision making, the instruction mostly describes some dynamical movements instead of the static images. So here we just provide another alternative to focus more on extracting such dynamical movements instead of the static images. So how to describe some dynamical movements? And here we just use a simple way, like if we have the image embedding of image embeddings of two different frames, and we can directly subtract them. And the subtraction of these two representations is already a direction. So we try to align this direction with the language direction. So here, the test instructions here actually become some visual dynamics directions rather than static frames. So for example, we can take this figure here, and the blue dot here represents the test representation direction, and the green dot here represents the image representation. And we can see that although the first image is far away from this test representation, but its transition direction aligns well. It's parallel to the language instruction, and we measure the similarity between these two representations as the concept similarity. So in this formulation, the transition aligns well with the test instruction, and that's enough because language mostly describe the dynamic movements instead of the static images. So, and also we can see that under both of these reward reparameterization methods, all the middle frames are canceled out. So this means we do not need to calculate all of the intermediate image embeddings to calculate the reward summation. We just need to calculate the two frames, the begin frames and the end frames. So the objective can easily to scale to long trajectories. So we can easily select the segment length. We can randomly select different segment lengths to simultaneously extract the global task progressions by compare the long segments. And also we can extract some local or some detailed transitions by compare the short segments. So basically, this is our DecisionNCE learning framework. And by adopting the implicit preference annotation, the reward reparameterization in embedding space, and also random segment sampling, and we can transform the Brad-Terry model, the reward learning objective, into a repetition learning objective. Okay, we can train on the diverse out-of-domain human video or cross embodiment robot video, and get a multimodal encoder, and then we can use this multimodal encoder for a lot of interesting downstream works. And before that, we first check whether our repetitions can clearly identify the matched trajectory and the matched languages. And here we visualize the heat map of the learned rewards for different instruction and segment pairs. And the diagonals here denotes the matched trajectory and the instruction pairs. So we can see that both DecisionNCE P and T can clearly identify the correct matched pairs and unmatched pairs. Okay, so and we also provide a lot of interesting analysis about how DecisionNCE can naturally ensure temporal consistency in the embedding space, and also it has a good embedding structure, and that yeah. So if you are interested in this part, please check our paper for more analysis. And then we just to further validate the effectiveness of the repetitions, we deploy our representation to solve many downstream decision-making tasks, like use it to train some language conditioned imitation learning policy, or use it to serve as universal rewards to run some planning methods. And first, for the language conditioned imitation learning tasks, we tested on 9 tasks. We just These tasks span a wide range of, including the fold, pick up, place, move, open, close, and flip, many skills. And basically, we collect about 100 demonstrations for each task, and we train one model to solve all of these tasks simultaneously, and given the language instructions and the conditions input to separate the different tasks. And we just for the model design, we just utilize the pre-trained multimodal reputations, and we then only fine-tune a two-layer 2056 multi-layer perceptions on this robotics domain. And here are some visualization of our policy rollouts, and the above are the average success rates across multiple seeds. And we can see that both DecisionNCE P and T can outperform the other reputations or the end-to-end trained RT1 on this data. Yeah. Also, we also test our method on the simulation tasks on the Franca kitchen environments. We just collect about only 1 to 5 demonstrations per task, and we train the policy. We can still obtain the relatively high success rates compared to the other base reputations. And we think this is because the simulation is quite simple, because no distraction here, and the initial position of the robot and the target of the goal position is always fixed. So these experiments are relatively simple. So we only need 1 to 5 demonstrations to solve this task. And more importantly, because DecisionNCE is adopted from the predatory model to train the rewards, so it can naturally serve as some universal rewards for downstream policy learning. And for example, if the video and the language aligns pretty well, we can observe a monotonically increased reward to reflect these correct task progressions. Okay. And this correct task progressions can also generalize well to from the same human embodiment to the unseen robot embodiment. We can still observe correct task progressions here. And more interestingly, if the video and the instruction are contradicting, that is, for example, the video here is a human pull down the tongue, but the instruction here is take tongue. So the DecisionNCE can output monotonically or just a decreasing reward to show that the progression is contradicted to the language instruction. So after this, we just use this reward to run some language reward MPPI some planning method in the Franca kitchen simulation reward. We use the simulation as the true dynamics and use our reward as the optimization signals to select the best trajectories to execute the task. And we can observe that even the DecisionNCE is not trained on this simulated domain, we still have about 10% to 12% success rate to execute the task. Yeah, solve the task. So, but we only train our downstream policy on a very limited or very narrow robotics data set, like 100 demonstration per task for the real robot task data set, and only 1 to 5 demonstrations per task for the simulation environments. So the limitation for our method is that the generalization ability is very low. For example, to train a generalist robot, the ultimate goal is we just deploy the robots in the open world solve the open task. So the robot must encounter many unseen objects or unseen scenarios in the real world applications. So the generalization ability of the robot is very critical to achieve the ultimate goal of embodied intelligence. And here we can observe that if the view here, the robot view, contains many distractors, like the goal is pick up the red cup and place it in the civil pan. But here are many objects that also is red. So here the robot will be distracted by the other objects in the view to just fill the task. And this thing also happens for other tasks. So we wonder how to further utilize the out-of-domain data to fight against the distractions faced by the embodied agent. And then we propose the instruction-guided visual masking. And this is my joint work with Jinliang. And this paper is also selected as an outstanding paper at the MFEAI workshop at ICMO 2024. And then please like Jinliang, to share this work to you guys.
Okay, so thanks to Jianxiong for his introduction, and it's very happy to be here to share our recent work instruction guided visual masking. Yep, and just as mentioned by Jianxiong, we can easily find a well-trained policy failed when visual distraction increasing, right? And we find it's not a problem for robotic control exclusively. So please move to the next slide. Yeah. And here we can also find the current most advanced large multimodals like GPT-4. Also face the same challenge. So here we give some examples. Given these images, given this image, it's a very high solution image with complex visual information and tiny objects. And we try to ask GPT-4V 4 questions based on this image. And we can find for each question, like how many, like this Q3 here, all the plants in the picture green. We also require visual information from a small portion of the original image. We find the GPT-4V answer for this question is wrong, right? And in contrary, if we try to mask the instruction on relevant parts of the image, and we can find the GPT-4V's answer becomes helpful and correct. Okay, so some of you may have realized that we are arguing that existing large multimodals, including robotic control models, they lack of enough visual grounding capabilities. They often fail to find out instruction relevant parts in image, and so they can't follow the instruction correctly. So we just attribute this problem to end-to-end training framework, as end-to-end training requires abundance of data, and they just require models to learn visual grounding capability through through this data implicitly, and we think it's just inefficient. So we try to develop a model, and this model can be, maybe we can firstly train a model, and this model is trained with explicit visual grounding integration, and then we can deploy this model as plug and play tools to enhance the downstream models, just like the robotic control model, to better follow instruction. So that's what we do in this paper. And in this paper, we just call it instruction guided visual masking, and we term it IVM. Okay, so so IVM is just similar to those traditional visual grounding tasks, like semantic segmentation and the referring expression comprehension. And recently proposed a very famous work called LISA, and it just proposed a task named reasoning segmentation. That is, it will give complex instruction, and they try to do segmentation task based on instruction. And however, while traditional visual grounding tasks focus on locating specific objects which are predefined or described by some simple language, our IVM task is more challenging. right? Because we are trying to infer the instruction and find out all instruction relevant portion in the image rather than some specific items. So just like this slideshow, we can find our IRM model just can work in this complex scenario, and the previous work cannot do that. Okay, and so training such a good IVM model is non-trivial, and the main challenge here is lacking of training data. We just require data consisting of images and the diverse language instructions and the corresponding pixel level visual grounding labels. And this kind of data is very rare, right? So to mitigate this issue, we just propose 2 automatic data generation pipeline to make existing open source data available for IOM training. So the first pipeline is for those data with visual grounding labels, and this data often lack of diverse instructions. So we just utilize large language models here to generate diverse instructions based on the given object type or the simple language. And this is the first pipeline. And the second pipeline is for those unlabeled visual instruction from training data and the robotics data. For this data, we got the instruction, but we do not have the explicit visual grounding labels. Pixel level is visual grounding labels. So for this kind of data, we utilize large language models again. We try to decompose the complex instruction firstly, and then we just utilize existing visual grounding experts, and to achieve the best performance as we can get, we just try to utilize a mixture of visual grounding experts to generate high quality labels for us. So we believe it's the best possible automatic annotation pipeline as best possible. Yeah, we just try to emerge knowledge from existing models as much as possible. Even so, the labels here are not totally trustworthy. So we just try to further improve the data quality. So we randomly sample 10,000 image instruction pairs from visual instruction training and robots data, and we manually label them to inject human knowledge here. Yeah, and this is really a huge work. And finally, we construct the IVM mix 1 million data sets by merging the machine generated and the human annotated data. So let's take a closer look at our constructed data set here. We just try to visualize the number of samples from different data sources with different proportions of the image related area within the image. So we can find the most images contain many distractions, making it very difficult to follow specific instructions. So it just highlights the necessity of proposing IVM again. So now we have enough training data, and the next 2 questions are what is the model design and how to train it efficiently on the generated data. And for the first question, I will briefly introduce our model design as the slideshow here. So as IVM requires strong reasoning capability to infer target area in the image, and also it requires pixel level awareness to generate the prediction. So we utilize pre-trained large multimodals for the reasoning, and a SAM encoder here for extracting dense visual features. And then we can take these 2 features and feed them into a transformer-based generator, and then we can get a final prediction. So that's our model design. And then let's move on to the second question, how to train the model efficiently. Of course, pure supervised learning is a good choice as we have labels, right? But might not be the best choice because our data are mixed quality, not totally trustworthy. So here we just inspired by recent advances in offline reinforcement learning. We try to introduce a training algorithm called discriminator-weighted self-supervised learning. That is, we introduce an extra discriminator and train it to distinguish the human and the machine-generated data. And then we can just assign the confidence outputted by the discriminator as the training weights for each sample. Okay, and then we just provide more details about our training framework. So for the discriminator training, it's just like a binary classification task it just requires to distinguish the human and the machine generated data. And for the IOM training here, we just follow the loss from segmentation task and assign a dynamic weight for each tempo. Okay, and we just do many ablation experiments to demonstrate the effectiveness of our training framework, and the results show here just demonstrates our IOM model. Our IOM model can achieve the best performance with the discriminator weighted supervised learning on the full IOM X 1 million dataset. Okay, so I think I have finished the introduction of our methods, and then let's see what our IOM model can do and what it can bring to downstream tasks. So for robotic control, we just deploy the IOM model by replacing the original visual input with the IOM masked image. That is, we just replace the policy's input. So we can find by replacing this visual input, the policy is quite robust to visual distractions as it cannot see them, right? And even we just here are some human interferences, and we can find the policy can also retain a comparable success rate as the visual distraction increasing, and even with human interference. Okay, and that's results for real robots. And then let's move on to the results on VQA-like tasks. Just as I just as mentioned before, the existing large multimodals, just like G4, we also face the same challenge. So we try to deploy IOM to enhance their performance on VQA-like tasks either. And here we just try to validate the IOM model with commercial chatbots and open source vision large language models here. And for commercial chatbots, we choose GPT-4V here, and we validate them on a recently proposed challenging benchmark named the V-star benchmark. And this benchmark consisting very high resolution images, and their questions are mainly about very tiny objects in image. And we can find with the IOM, with the help of IOM model, GPT-4V's performance is very significantly enhanced by our IOM model, right? And for the open source vision large language models, we try to integrate our IOM model with Lava here, and we also validate them on 6 classical VQA benchmark here, and we can also find the performance consistently increased. Okay, so these results on the on such benchmarks, and we also provide more visualizations to display what can IOM do. So for different types of questions, IOM can infer the target area in the image, and even it is a very small portion of the original image, and it just demonstrates amazing reasoning and grounding capability. So we will soon publish our datasets and the well-trained IOM model, and welcome to explore more about IOM model by yourself. And I think I have finished my introduction about IOM model, and I hope our IOM model could be helpful to you. Okay, so maybe I think we should let Jianxiong to make a brief conclusion about our presentation. Thank you. Okay.
Okay, so and last, I will just give a brief conclusion about our these two works. And for DecisionNCE, we just try to utilize as much as possible the out-of-domain human or robot data to train good representations, and then utilize the valuable information in the representations to improve the downstream policy learning, like imitation learning, planning, or perhaps reinforcement learning. And for the instruction-guided visual masking, this work, we just try to use as much as possible out-of-domain vision question answering data to directly enhance the visual grounding ability. So both of these two works are trying to utilize as much as possible data to improve the robot learning. And in fact, you know, in the physical world, the collecting data is really challenging. So why don't we just utilize all the available data to train a robot? You know, for the robot, you need to understand the human instructions. So you must understand the language modality. And also you must understand the environment through the visual input. So you should also understand the visual modality. And last, you need to execute the robot, give command to the model just to execute the task. So you also need the action modality. So why don't we just try to utilize as much as possible data in the internet to train a robot, to improve the robot? And so embodied data are quite limited, and try to absorbing out of data to enable the generalizable and the sample efficient embodied AI is very critical. And basically, that's all about today's sharing. And thanks for listening. And these are the two the QR code for our papers and the codes. Yeah, thank you.
Thanks for the great presentation, guys. It was super interesting. I think we can open the floor for questions now. Maybe I will start with one. I was wondering, have you tried for the second paper when you do the masking? I think it's a really good idea, and I was wondering if you tried when in settings when you have like multi cameras, because we see that I mean a lot in for autonomous driving, but also for robotics where you have more than one camera for the robot, and it feels like a technique that that you're using could be even more effective when you have a lot more cameras and a lot more pixels to deal with.
Yeah, actually, this is a very interesting question, and we, you know, during the training of the IVM model, we manually label a lot of robotics data from the OpenX embodiment to let the IVM model can generalize well in the robotics domain. But typically, this the view we trained for the IVM model is the third person view, like this kind of view. But we never trained on the wrist view. Like if we have one camera mounted on the wrist of the robot, we don't train IVM model on that view. But during the inference, we feed this wrist camera view into the IVM model, and we can still see that the IVM model can accurately highlight the instruction relevant objects and ignore the others. Yeah, so perhaps this is because the high generalization ability of the large vision language models. Yeah.
So this sort of emergence of the multi-view generalization, because it's able to mask even from like a different kind of a camera, it's able to mask correctly the object.
Yeah.
Oh, okay, that's really impressive. That's really cool. I think there's a question from Alex. Alex, you mute yourself and?
Yes, thank you. Thank you for a really inspiring talk. So my question really is asking you to speculate about extensions to the model, and in particular to the task where you're aligning video segments with language. So you focused on individual instructions basically in that part of the work. But what users will do with robots will do things like make lasagna, boil the pasta, make a bolognese, make bechamel, assemble on a thing, right? So what's happening there is there's a structure, what's known as a discourse structure to the complex instruction, where making lasagna is then elaborated with these more specific instructions. And users will do that to express their preferences on how to do a big complex instruction like make lasagna or clean the kitchen and or make coffee. In terms of video alignment, the make lasagna segment sort of matches the structure and its relationship to the segments for the elaborated instruction with the bolognese and so on, it sort of reflects that structure, right? So my question is, suppose the large language model actually does a pretty good job of encoding discourse structure. In other words, of recognizing that the sort of bolognese pasta instructions elaborate making lasagna. They're part of the instruction of temporally part of the instruction of making lasagna. And that's a big ask of the large language model, but pretend it does. How could you use that to get the right segments in a discourse-based instruction like that?
Okay, this is a good question. So
I
basically, you
realize
mean
this is I actually think it's an unfair question because I'm asking you to speculate, but speculate anyway.
So basically, you mean sorry. Actually, I didn't exactly follow your question because yeah, you know. But what I understand is that you mean the language instruction is highly complex or something like that.
The way users will instruct robots to do things won't be
Yeah.
simple instructions where I'm telling you one thing after another. I will be grouping instructions into sort of discourse segments which summarize the big thing I wanted you to do, which I introduced in the first place. So I could say, make me a cup of coffee. I I'd like use the espresso machine and then add milk.
Ah, okay, I see. So you mean these two language instructions describe the same thing, but in the language world, they are different. So how to...
Yes, exactly.
Yeah, and this is
Users
one
are not going to just say, make me a cup of coffee,
yeah,
nor
yeah.
are they going to say, use the espresso machine, add
Yeah,
milk.
actually, this is
They're
a
going to
very
say
good
both.
question.
All right.
Yeah. You mean, you know, so basically we use the contrastive learning objective to train the representations. Okay, so we must have some positive segments, positive points or some negative points. And in the training of clip, the clip model, and actually they also face the same issue. For example, an image of a cat, or you can describe the image with one cat, or you can also describe it in another more complicated way or other detailed way. The image is same, but language are different. So how to choose which one is the negative, or actually they are both in principle they are both positive language, but they are different. And yeah, we also have the same problem to train the repetitions, but the answer is somewhat, you know, the positive, because when you have enough diverse data to train a contrastive learning objective, and the model can somehow get rid of such noise. Maybe this is some kind of noise because they are different language representing the same thing. But if you have enough diverse data to train that contrastive learning objective, your model will generalize well to handle well on this noise data. And actually, we also observe some cases in our paper, like the instruction for the first video segment is open refrigerator, and we found another language instruction in our data set looks like only open the refrigerator. So the only difference between these two languages are the V, but they are treated as two different language. And so yeah, noise actually exists during the training of the contrastive learning, but with enough data and diverse data, yeah, this problem can be handled well.
Yeah, that's not really answering my question. I agree. There are paraphrases to open the refrigerator. You know, it could be open the fridge door, open the refrigerator. pull the handle and open the refrigerator. There are many ways of expressing that action. I am rather talking about the way language is structured. In other words, make a cup of coffee, and then I drill down and tell you how to do it, okay? In a discourse, in a multi-sentence discourse. And if large language models can recognize that semantic relationship between make a cup of coffee, I like it with milk, or, that adding the milk is part of making the cup of coffee, right? There is a temporal part-whole relationship that is implicit in the discourse, in the events described in the discourse, which affects segmentation, right? Because you're temporally aligning video segments with the denotations of the actions. Can you use that? Can you use that to extend your model? I mean, maybe we should take this offline because I'm really dominating.
Yeah, I think. Yeah, I think this is. Yeah, I think this is a good question, and yeah, maybe we can use some techniques to find the semantic similar thing, or some highly related data together to train the model instead of only just brutally treat them as different tasks. Yeah.
Thank you.
You're welcome.
Yeah, I think this is quite an interesting point. The how to disentangle, like, language is not necessarily temporally consistent, but so the prompt won't be temporally consistent, but the action plan must be, and the way the robot acts in the real world must be temporally consistent. Yeah, that's quite interesting. I had a slightly different question on. So I'm a little bit familiar with the work from Jason Mao, VIP. I believe it's the value implicit pretraining. I think it's one of the baselines you use. Could you give some intuition on the difference between DecisionNCE and VIP, and what DecisionNCE does that improves over VIP? Because I see in your result that it does better.
Yeah. So the first difference is the VIP only considers the vision, only the visual modality. It's a unimodal encoder. When you train a VIP, you just consider the visual modality without the language modality. But our visual representations are semantically meaningful in the language space, because we are trying to align the visual progressions towards the language goal. But in VIP, they just simply try to find some coherent or some inner temporal consistency within a trajectory, but not it cannot push the different trajectories together. For example, for DecisionNCE, you have one language instruction called open refrigerator, and you have many diverse visual images, different background, different views, or even different embodiments try to doing the same task called open refrigerator. DecisionNCE will not only ensure the inner temporal consistency for each trajectory, it can also push pull different trajectories of the same semantic task in a very near space in the representation space. But for VIP, they just align around the entire representation space with no semantic. I see that the cluster, they don't have the cluster effect, and this is one reason. And the other one is that VIP actually uses reinforcement learning to train the representation. So when you want to use RL to train something, we must first design a reward function. So in VIP, the reward function is designed as the negative -1 for the non-terminal state and 0 for the terminal state. So this reward may not be the perfect to train a policy, and also the VIP uses the L2 distance as the measure between two representations, because VIP only considers visual modality, and it's okay in the unimodal setting. But here in our multimodal setting, we chose cosine-similarity as our measurement about the distance between two representations. And by doing so, actually the space will behave better than the L2 distance, because L2, if we want to maximize the L2 distance between two representations, the network can do it in a very easy way. It can just directly pull away from these two representations, and the L2 distance will be very, very, very large. But so this will result in a not well-structured representation space that can improve the policy learning. But if we chose the cosine-similarity, maybe the stability and the structure of the representation space may be better. And this is basically the three about some high-level differences, and also some technical detailed reasons about why DecisionNCE is better than VIP. And also, actually, the most closest work to DecisionNCE is not the VIP, but not the LLV. Also from Tsinghua. LLV just adds one clip loss at the end of the VIP loss to transform the VIP objective into a multimodal representation learning objective that it simultaneously minimizes the VIP loss to extract the temporal consistency within one trajectory, and it also tries to align the final image with the corresponding language instruction in the embedding space. So yeah, this is similar to DecisionNCE, but I want to say is that for decision-making task, the language instruction mostly describes some dynamical movements instead of only the final image. So the instructions are mostly like open something, move something, or push something. So it cannot be simply described by one static image. The static image can only describe one opened refrigerator rather than open the refrigerator. So basically, this is one core difference between LLV and VIP and DecisionNCE. And DecisionNCE tries to align or try to extract the dynamical movements in a video, but the LLV only try to align the final static image with the language instruction. And this is not preferable, maybe not the best choice in the decision-making setting. And that's core difference to the LLV.
All right, thanks for the very thorough answer to that. I think specifically on the you point about the cosine similarity and the L2 distance and how it changes the representation to go from one or the other. I also encountered similar behavior when training state representation for RL agents with representation loss like Miko, for example. It seems that the L2 distance is too constraining for the representation, because it forces the entire representation to be dedicated to the objective, basically. Whereas if you do cosine, you're only constraining the angles to embed the information, and so the magnitude of the vectors are still free to have a different meaning. And it seems to be quite important as well. What's your intuition on, like some people in RL, they use projectors to avoid that as well, or like not even in RL, in a lot of like pre-training, unsupervised pretraining or supervised pretraining, they use a projector
Yeah.
network so that you also absorb this sort of you make your actual space less constrained because you optimize in the projection space. What's your intuition on using that versus using cosine similarity directly in the representation space? Is there like times when you should go for one and not for the other, or is it more of a just let's try both and see what works?
Maybe you know, actually a lot of tactics insights are adopted from another domains like neutral language processing or computer vision, and actually they have done a lot of experiments to test which kind of metrics are more suitable for training larger models. You know, for example, the cosine similarity versus L2 distance, or when you train the Q function, we typically use the L2 distance as the loss, as the measurement, as the metric to measure the difference between the target Q value and the current Q value. But somehow in recent years, there are many researchers that tell us, no, you should don't use the L2 distance. It's quite unscalable, and you need to try some another laws like cross entropy to treat the Q value not as the regression problem, just treat the Q learning problem as a classification problem. It will be more stable and suitable. So my opinion is that maybe we can, if you really want to train some very large and scalable representations or models, maybe perhaps we should utilize the something like a cosine similarity or the cross entropy. We need to adopt some useful insights from other domains that they have do a lot of researches in the large model domain. So we need to learn from their experiences. Yeah, maybe that's my opinion.
Oh, fair enough. Yeah. I think there is a one of the papers at ICML, like the sub-progressing paper, but that seems to go also in that line of it seems that like there are many different things we need to do to like unlock scaling in RL. Because still today, when you try to scale like for example, the Impala architecture, there is a point where you stop getting any returns. Actually, you lose performance, which is kind of unique to RL in terms of in the machine learning space. Awesome. Do we have any other questions from the audience? Okay, I don't think we have any other question. But that was a super interesting talk, and I really enjoyed the discussion afterwards as well. So thank you so much for coming to present. And hopefully we'll be following your work. So hopefully we can get you guys again when the follow-up comes up.
Yeah.
All right. Well, so thank you all for attending as well, and well, see you next time.
See you.
Bye-bye.
Bye-bye.